Okay, the record is on. Ladies and gentlemen, welcome to the class today. And of course, we are pretty much done with the tension members. So now today we are going to start talking about compression members. So please remember that we are still in the category of the two force member. Maybe I can say that. Let's say it's a member under the axial force. Before this, we talk about when the member is under the axial tensile force. So today we are going to try to understand when the member is under the axial compressive force. So the force will be applied through the centroid of the member like that, okay? But instead of tension, it's now compression. Now, before we say anything, please keep in mind that what we always do is this. So I always repeat this at the beginning of each topic, okay? Remember that we have the demand and we have the supply that we need to make it meet the demand. We are going to make sure that the resistance of the structure is always greater than the load that is provided by the load, okay? So now, today we are going to start talking about the resistance of your structure under the axial compressive force. So again, we are going to, let's say, this is the word that you should always use, predict the strength of the compression member, okay? We can revisit this a little bit, you know, in the first class last time. This is the key thing. Okay, we talked about this, and it is always applicable, you know, the load and the supply, and demand and supply. Okay, but today, let's say we are going to talk about the prediction of the compressive strength, let's say, of the compression member. Now, the reason why I use the word predict, you should know by now that we cannot really know what's going to happen. So we have to try our best to predict the strength of our structure, okay? And the most important step is to, what do you think it's going to be? Understand the behavior. It's English. It's American wouldn't have you, right? You must understand the behavior before, you know, you can predict anything. You must understand it first, right? Just like, let's say I'm going to ask where one of your friends is going to be tonight. You know, he loves drinking, so you predict he's probably going to be in this, you know, liquor store and drinking with some friends, because you understand his behavior, right? So you can predict where he's going to be. Then likewise, we need to understand the behavior of steel under compression. That's what we need to do. Okay, and once we understand the behavior of steel under compression, we should be able to predict the compressive strength of the member. So regardless of what you do, understanding the behavior of the material is the most important step always. Now, let's say previously, tension. Behavior of steel. Let's cut the U. Behavior of steel under tension is that when you apply tension, it's going to yield or rupture, right? Very simple. So that's why we can predict the strength of the tension member without any problem. But when it comes to compression, you see the behavior is that from the video clips, you don't see any material being destroyed, right? Because steel is ductile. So you are not going to crush steel just like you crush concrete. When compression is applied, the steel will not be crushed, but instead it will lose stability. Okay, when the steel loses the stability, the stress where, let's say, instability occurs is F critical buckling stress. And because, you know, you can see from the video clip that you push the concrete, you apply compression. I'm sorry, when you the material, not concrete. I'm sorry. When you apply compression to the material, it's sort of move to the side, as if it was being bent, you know, as if there was bending moment applied to it, and that is correct. Okay, and so when the buckling, I'm sorry, when the member moves to the side under the influence of the compression member, we call that behavior buckling. Okay, it's called buckling. Say when the instability under compression occurs. And the most important thing is that when it occurs, chances are the stress where instability occur or F critical will not reach Fy. So in order to predict the strength of our compression member, we must understand that steel is a ductile material, therefore it will not be crushed. It will lose stability instead. And when it loses stability, chances are the stress in the material will not reach Fy. So you can see the major difference here. That is, under tension, you can predict that the stress at which failure occurs will be either Fy or Fu. So you know the stress. But for compression member, because of this stability problem, we will not know the critical buckling stress. So that instead of being something that you know, it becomes one of the unknowns. Is there any question on this one? No, I suppose. So here, it's been introduced by the video clips that the buckling is something that may occur under compression like this. And when it occurs, you see that your member actually moves as if it was under bending moment. But keep in mind that your member is undertaking compression. Okay. So this is it. Again, the reprise of this. See very clearly how it loses stability, moves to the side. Okay. So now you have had this before in your mechanics of materials class, that when your compression member has a considerable length, it loses stability. So the question in that class is that what is the load that causes instability? So again, you can apply the double integration method. You write down the moment equation, which is, you know, when I cut the free body diagram, because P now, the two P's do not coincide now. So to complete this free body diagram, you need to have moment to help out. So you can write this moment equation, you know, and this becomes the deflection of your compression member. So you can write down the moment equation, which is going to be equal to the second derivative of the deflection multiplied by EI. And then the moment itself is going to be equal to P multiplied by the deflection. So that renders this problem into what you should have known by now, that it is a differential equation. So you need function to solve this. And it's a trigonometry function. If because you didn't hear the first clip, the professor mentioned that this is perfectly the sine curve. So you can use the sine function to obtain the solution of this equation. And that leads us to elastic buckling load, which can be approximated by this formula, I square EI over L square. And notice that I mentioned in the second clip that, when you have the two axes of your cross section, your compression member always bends in the direction that has, say, weaker moment of inertia because it has equal length, right? But we can say that when we change this into the critical buckling stress, this becomes a term where we always refer to as the slenderness ratio. Okay, slenderness ratio. The slender the member, the less load carrying capacity it is going to have, and it's going to buckle much more easily. And when we talk about, say, from the clip, you see that she has the cross section that looks like this. So this angle is very strong, right? So you cannot bend your member about this axis, but this axis is going to be very, very, very weak. So it bends about this axis, just like your plastic ruler. So when you have the cross section that has two axes like this, you must check which axis is weaker, or I can say which axis is more slender, and that slenderness ratio is going to dictate the behavior of your member. Okay, from time to time you can have the cross section whereby you only have one, like this, a circular section. There's no weak or strong axis, right? There's just one L over R, that's fine. Or square section, but in general case where you have two axes, you must check both. Okay, so that's now you are beginning to get the big picture of the compression member made of steel now. Compression is going to cause your material and therefore your member to become unstable. Okay, so your member and your material will not reach yield strength. It will suffer from instability first before it reaches there. And so we can say that I may come back and explain a little bit about this in the future, but not now. The first one is called the buckling of the entire member. As you see from the clip, you can say this is a global buckling. Of the entire member. And you see from the clips that it may depend on the support condition. Another thing that it may depend on is the shape of the cross section. In here, the three buckling modes are represented. First one is called lateral buckling. It moves to the side, which is the main failure mode that you will learn in this class. This is also called flexural buckling, because your member will buckle as if it was under bending moment, but in fact it is, right? From this free body diagram, it buckles under bending moment, even though it carries the compression. Okay, now it moves to the side, and we call that flexural buckling. This occurs with the cross section that is doubly symmetric. You know what I mean? Doubly symmetric section. It is when your section is symmetric in both X and Y axes, like this. Okay, X axis is symmetric, right? And so is Y. So an H shape, which is our main section here, is generally doubly symmetric. You say H is doubly symmetric. You can say the rectangular section, square section, circular section, they are doubly symmetric. Okay. Now, if the shape changes into something, for example, like a cut T. Cut T has one axis of symmetry, which is the y-axis. X is not, so it's going to have another buckling mode that's called flexural torsional buckling, but we're not going to talk about that in this class. And doubly symmetric can have another one that is called torsional buckling, where it twists by its own principal axis. But let's say this will not occur with the sections that we are dealing with, which is hot roll, doubly symmetric. But when you build the columns from plates, you may have to check this. Okay, but again, it's not the focus of this class. This is way too much. Another one that we will talk about later on is called local buckling. Now, local as it is, it means that some buckling may occur locally somewhere at some specific point in the member. For example, like this, the flange may suffer buckling in some location, not the entire member buckles, but just the flange in some location, or the web. So there are two possible failure modes of compression member. First one is the buckling of the entire member. You may call that the global buckling, or to be more specific, it's a lateral buckling or flexural buckling of the member. The second one is when some of the elements of your cross section are too slender, such as a flange, one of the flanges, or the web. So they may buckle before the member buckles. Okay, so two things, two possible failure modes. So that's the behavior of our steel material under compression. Question? Is there any question? No? Fine. Now.
Excuse me.
Yes, please.
According to the video, I see that the support, the pin support, it rotates about its weaker axis. But what if we install?
It's not possible. Maybe it's a problem with installation, because that's why I sort of assumed that the second video clip was done like for the term project, student term project, because when we talk about this, the ability to rotate in both axes must be equal. Okay, and when let's say you can imagine your plastic ruler and you apply compression, it's impossible that it will buckle, in another axis, in the strong axis. Can you imagine that?
Yes.
So maybe it's just because you can, if you can recall, the percentage of the error is like humongous, 50%, right? So well, I think she did a good job in demonstrating the support condition, but on that maybe not so well. Anyway, but understand that it's a work of an amateur. Okay, so please don't have any bad feelings towards the video.
Yeah, but I just want to ask if the real pin support we use in the design, is it going to be able to rotate all in all axes?
Good question. You want pin, you better make sure that you give detail to the structure so that upon construction it should be pin. Correct? Remember, we are engineers, so we can dictate the behavior of the structure by giving proper details so that it behaves the way we want. But that is one thing. Another thing that you should look at is that it is difficult to have the real pin and the real fix in the real world. If that's what you're asking, because let's just say I want my beam. Okay, now this is off topic a little bit, but I want to create a simple beam. So that means at these two supports, your member must be completely free to rotate, correct? That's your simple beam. So the question is, can we really have that? Or say, I want this. I want both ends to be fixed, you know, just like the fixed moment, stuff like that. Can they really be completely fixed? So perhaps not. So, you know, because I think this is a very good question. So let me try to explain it right away this time. First, let's say for steel structure, I don't know much about concrete, but for steel structure, when you want to build simple beam like this, the way you give details must ensure that, say, large enough rotation can occur. They used to give the number in the specification, say 0.3 radian. It's not like it's gonna rotate freely like that. No, there's no such thing. But they say in order to be considered a pin, your detail must be able to give 0.3 radian. And so they have done a lot of tests and so on and so forth, and they have, say, the given you some details that will work as a pin support for sure. So you can use those details and be sure that, okay, it's going to behave like this, but it's not going to rotate freely. The definition of the steel structure is that if you should be able to provide at least 0.3 radian. Okay, that's for the pin. For the fix, I have seen the paper a long time ago that they really could create fix. Just add the steel plates to make the support super really stiff. It's possible, but it is very expensive. So they have, again, the details. Okay, if you connect, say the parts of the member where it transfers the moment, that becomes the fixed support. So it is quite, I think I say it's exciting to know that now this step that you are going to make, just you're going to make this come true. It's not like a pin, a roller on paper anymore. You will learn in the future how, in fact, you could really make the structure behave that way. All right. Hope that answers your question. Very good one. You know, you now you should know why I name my channel "Talk to the Structure," right? Like that. Okay. So is there any more question? I really welcome them. You know, I think the more you ask about it, the more we discuss about it, I think the more you should feel the behavior of the structure. You know. So all quiet. So let's say now we are going to look more closely to the buckling behavior of the structure. Okay, now remember that we use steel and the material itself is like this. So let's look at the first behavior first. Let's say we put compression on the member, but the stress does not go beyond the elastic limit. So the first one that we are going to look at is the elastic buckling. The buckling of our compression steel member when the stress is not beyond the elastic range. Okay. So what's going to happen is this. Yes. I suppose this formula is applicable. The one that you got from your mechanics of materials class, the elastic buckling load, pi square EI over L square. Okay, and when you plot this, you're going to get this one. This is called the Euler parabolic curve. Okay, but notice that you know the stress now The critical buckling stress is a function of the slenderness ratio. See that, right? And you should see one more thing, that is, if L over R approaches 0, your critical buckling stress approaches infinity. And this approaches 0. Okay? Which, you may think, is it possible? But remember, we are talking about the elastic alone. But in the real world, you are going to, after you keep applying the load, you are going to move your material into the inelastic region. Okay? Now, stress is going to change because you are no longer in the proportional limit. So 3 things that we must consider to predict the strength of our compression member with the behavior in the inelastic region. First, see, it's going to flat out. So that means your member will not go on forever. It must yield at some point. Okay? It must yield at some point. Second, because of the manufacturing process, we are going to have the, let me erase this one. Why? Oh, okay, so the arrow for the inelastic region. Residual stress. This is due to manufacturing process. Okay? Residual comes from the word reside. You guys know the condominium, right? They call the residential area. So reside means to stay. Residents is the people who stay in the residential area, right? So the residual stress is the stress that stays there even before you load your structure. So it's there even before we have the load. And even though finally we may reach this plateau, but it's going to cause the deviation here, that instead of going direct route to the yield and then, go on like this, it's going to deviate the stress to a different path before it goes down. So when you are somewhere around here, you must deduct the load carrying capacity of your compression member due to this as well. The third one is called out of straightness. Simply put, the column may not be perfectly straight. It may have some, crookedness, very, very small, very, very tiny. But the research, some research has shown that only a tiny amount of this, say, initial deformation may reduce the strength of your member dramatically. So we must account for that. Okay, so this is a professional work now. We are going to design the compression member. So therefore, we must take into account what the worst case scenario we may have. And in the inelastic buckling, which is going to be the behavior that you are going to deal with more than elastic. Because think about it, the elastic, it just when your member is elastic, it means the load is so small, right? Because elastic means that once you unload your structure, it should go back to the original position. So the load is small. So generally, we are not dealing with that at all. We're dealing with this more. And when the steel member undertakes compression and it is going into the inelastic behavior, you must be aware of the fact that could yield the residual stress, the stress that comes with the manufacturing process may affect the load carrying capacity of your member. And you have to also take into account that your member may not be really, really straight. Okay, is there any question on this? Yes, not. So here, from the from the Euler buckling stress, the original curve, you know, in the elastic region, you can cap this off because, you know, the material is real and therefore you can't load it beyond the yield, right? It has to yield. So it has to be capped off at some point, not to exceed the yield stress. Now, the effect of the residual stress comes from this, you know, because predominantly the member that you are going to use is called hot roll. So it's hot roll means that, you know, they use heat to roll the steel into the shape. And once it is hot, you have to, you know, leave it to cool down. And when the cool down process takes place, you know, at the tip of the flange here, it will cool first. But when the cooling process, it keeps moving inside, when it wants to cool down here at the junction, because it is connected to the flange on the opposite side and to the web, so it becomes difficult for it to cool, and therefore this will create the stress right there in the member, because the whole section cannot cool down at the same time. And you can see from this picture that you see it curves up a little bit on both ends. But that is what we call the residual stress. The stress is already there even before we have the load on the member. Okay. Now the last one is out of straightness. So I have mentioned the initial deformation can cause the major load carrying capacity reduction. And so they introduced the one factor to simply take into the account for this effect. Okay, so that's three things taken into the account. And they also have some kind of testing. And I see that, remember, this is Euler. They're not Euler. Euler. And that's Fy. And that's a test result. So it fits this curve. Okay. So we took the test result, which, you know, trying to figure out all those factors and fit them with the equations. But to do the curve fitting, they split this curve into two regions. Call that limiting KL over R here. And so you're going to have two regions to try to predict the strength of your compression member. Right here on the right, this is slender. So it's going to be based on the Euler. You see how the two curves go together. So this is the slender, because this is L over R, I suppose. But I'm not so sure, because yeah, they use the F critical over Fy to normalize it, but that's supposed to be it. This on the left side is inelastic. So they use a curve fitting. So we are going to have two equations with one limiting KL over R value to split the design region into two groups. Okay. All right. I'm going pretty quickly now. So this is it, ladies and gentlemen. Now, again, the nominal strength of your member is pretty much the same, right? It's a stress multiplied by the area. So that's the bottom line. Nominal strength is stress multiplied by the area. The area we already know, but we are now going to have to try to predict this by using the design curve. Okay, I think it ends the session ends nicely here. So it goes really quickly, the online session. So I'm just going to stop here and I'll come back and explain the equation in the second session. So is there any question? Hello? Hello? Question? So I'm gonna stop.